Materials Research and Technology, Defense 4.0. Aerospace and Defense 4.0 is the application of the Industry 4.0 technologies in the aerospace and defense industry. Developing new cost-effective products and services, making existing products smarter using sensors and connectivity, and leveraging advanced manufacturing processes such as additive manufacturing, among other objectives. Industry 4.0, or the Fourth Industrial Revolution, is the creation of a digital manufacturing enterprise that is not only interconnected, but also communicates, analyzes, and uses information to drive further intelligent action back in the physical world. It drives the physical act of designing, manufacturing, distribution, and performance in an ongoing cycle known as the physical to digital, digital to physical loop, or PDP loop. Throughout this cycle, real-time access to data and intelligence is driven by the continuous and cyclical flow of information and actions between the physical and digital worlds. Many organizations already have some portions of the PDP loop in place, namely, the physical to digital and digital to digital processes. However, it is the leap from digital back to physical, from connected, digital technologies, to action in the physical world, that constitutes the essence of Industry 4.0. The steps of Industry 4.0 are: first, establish a digital record. Capture information from the physical world to create a digital record of the physical operation and supply network. Second, analyze and visualize. Machines talk to each other to share information, allowing for advanced analytics and visualizations of real-time data from multiple sources. Third, generate movement. Apply algorithms and automation in order to translate decisions and actions from the digital world into movements in the physical world. Aerospace and Defense 4.0 has a multitude of current and emerging applications. Some aerospace and defense companies are already beginning to realize the transformative effects of these technologies. They are exploring significant potential value across a variety of dimensions, from cutting costs and restructuring supply chains to expediting time to delivery and making devices and products connected across the board. For instance, real-time flight data collected from sensors in an aircraft is being used to reduce fuel consumption, improve scheduling, and minimize flight delays. Aerospace and Defense 4.0 technologies are also improving the aftermarket experience by using data to track asset condition and predicting parts and systems failures beforehand. Aerospace and Defense 4.0 technologies. Additive manufacturing. From current applications, prototyping, tooling, and functional end-use parts manufacturing, to emerging applications, combining new types of novel materials to improve aerospace parts and accessories. Advanced analytics. From current applications, monitoring real-time aircraft health, identifying system/component failures in advance, making intelligent scheduling and forecasting models. To emerging applications, developing large-scale digitization of plane maintenance data and schedules, creating synergies across business and functional areas by enabling a new connected plane. Advanced robotics and cognitive automation. From current applications, using robotics in aircraft manufacturing for more efficient production with fewer errors and quality issues. To emerging applications, simplifying simulations of aircraft, weapons, and satellite performance, avoiding time-consuming analysis and tests of algorithms, software, and hardware. Artificial intelligence. From current applications, applying artificial intelligence to robotics, automatic programming of tasks and processes in industrial settings, and enabling predictive maintenance. To emerging applications, leveraging artificial intelligence and computer vision technologies to augment advanced safety features in aircraft, incorporating advanced artificial intelligence into drones, and replacing human co-pilots in new, autonomous aircraft. Blockchain. From current applications. Enabling greater transparency of information between different parties, improving just-in-time logistics, reducing erroneous orders, improving inventory throughput. To emerging applications. Improving tracking in supply chains and procurement, using a shared database with suppliers and partners, improving validation of supplier performance and reputation, and time-stamping records to reduce fraud and improve supply chain security. Digital reality, artificial reality, virtual reality, and mixed reality. From current applications. Replacing assembly manuals with smart glasses displays, which substantially reduces wiring production time. To emerging applications. Using virtual reality to optimize and design factories and simulate an entire factory or warehouse to train workers to use equipment more safely and efficiently. Internet of Things. From current applications. Monitoring aircraft engine health and optimizing engine performance based on data collected from sensors. To emerging applications. Managing material costs and demand fluctuations by analyzing big data, enabling integrated smart connected assets and operations, and, eventually, an autonomous production environment. Players that implement multiple advanced technologies will outperform and outcompete their industry counterparts. Materials Research and Technology recognizes the importance of making assets intelligent. Our most important asset is our people. Aerospace and defense companies need to recognize that in time, equipment gets to be more obsolete. On the other hand, over time, people with more gray hairs get to be less obsolete. Our know-how, and especially our now-why, allows us to be resistant to obsolescence. Investing in our most important asset allows us to compete and outperform our counterparts. Materials Research and Technology is your best partner in your Aerospace and Defense 4.0 transformation. Transformation can be achieved through research and development, innovation, technology transfer, and so many other ways. Materials Research and Technology is committed to research and development and innovation, devoted to developing skills, know-how, and know-why, so their customers and partners can leap to the essence of Industry and Defense 4.0.
What happens if we invest in developing our people and then they leave us?
What happens if we don't, and they stay?
Richard Branson said, "Train people well enough so they can leave. Treat them well enough so they don't want to."
Maintainability, reliability, and timely performance. Materials Research and Technology Performance. The innovative RCM. Materials Research and Technology mission: to develop independent research and development centers that serve as vehicles to perform sustainable, multidisciplinary, collaborative research, development and technology transfer between material research and technology and the rest of the sciences and engineering community. Materials Research and Technology Vision: to be the reference operations and maintainability, reliability and timely performance center within responsible industries. What is reliability-centered maintenance, RCM?
And as I always say, if it's not broke, don't fix it.
If it ain't broke, don't fix it. This old adage makes a lot of sense when we're talking about a hand-me-down car or a coffee maker that miraculously keeps brewing year after year. But when it comes to your company's most critical assets, this laissez-faire attitude won't cut it. Asset-intensive organizations rely on consistently getting the most out of each and every piece of equipment they own. They must develop a maintenance approach that's cost-effective while maximizing uptime and performance. By embracing a flexible, reliability-centered maintenance strategy, organizations can keep downtime to a minimum without incurring unnecessary costs. Reliability-centered maintenance, RCM, involves assessing assets individually and adopting a maintenance approach informed by and tailored to the requirements and the importance of each asset. Successful RCM keeps the cost of maintenance low and asset performance high. Maintenance strategies employed by RCM differ from asset to asset based on several factors. These include how costly and disruptive unplanned downtime would be, the importance of the asset to your organization, and the impact of asset failure on the environment and safety. Whether it's a crucial piece of machinery that would benefit from constant monitoring and predictive maintenance, or easily replaceable equipment that you can safely run to failure. Your organization can use RCM to evaluate and develop tailored maintenance strategies for every asset. Why implement reliability-centered maintenance? Reliability-centered maintenance aims to maximize asset performance while avoiding unnecessary costs and downtime. Here are just some of the benefits that can come with implementing RCM. Asset utilization. RCM cuts down on asset downtime by identifying how an asset might fail and addressing those potential failure modes by importance. This data-driven approach is the key to focusing your limited maintenance resources where they'll make the most impact, as well as performing required maintenance without resorting to unnecessary scheduled downtime. Cost optimization. Unscheduled breakdowns result in a heavy impact to your organization's bottom line, this due to lost production time and expensive repairs. And attempts to avoid unanticipated repairs can easily result in over-maintaining assets, wasting funds that could be better spent elsewhere. With RCM, you can intelligently keep assets performant with maintenance strategies that deliver the results you need at the lowest cost possible. Capital allocation. Organizations can effectively distribute and invest their financial resources only when they have an accurate read on expenses, including those associated with maintenance. RCM gives organizations a detailed plan for maintaining their assets and allocating costs, so leadership can make financial decisions based on data rather than guesswork. ESG compliance. Reliability-centered maintenance also gives companies the chance to revisit environmental, social, and governance (ESG) factors and guidelines. Complying with all relevant regulations, maximizing worker safety, and boosting sustainability are all concerns that receive due consideration during the RCM process. Digital operations. RCM meshes perfectly with digitized maintenance solutions that support work from anywhere. This allows for capturing and accessing data in real time, utilizing digital twin technologies that produce detailed virtual representations of physical assets, and contributing to a smart digital reality that seamlessly integrates the real and digital worlds.
Non-destructive testing, or NDT, is a wide group of analysis and techniques used in science and industry to evaluate the properties and integrity of a material, component, or piece without causing damage to the specimen or piece being tested. The terms non-destructive examination, NDE, non-destructive inspection, NDI, and non-destructive evaluation, NDE, are also commonly used to describe these techniques. Because NDT does not permanently alter the physical conditions of the piece being inspected, and it is a highly valuable technique that can save both money and time in product assessment, troubleshooting, and research. Some NDT methods include ultrasonic, electromagnetic, radiographic, remote visual inspection, guided waves, magnetic particle, penetrant testing, and others. All these methods have been subject to significant improvements during the last decade, therefore, making now available more accurate tools in the field of materials examinations. The Materials Research and Technology Group started researching in and applying non-destructive testing since 1981. Materials Research and Technology and its sister company NDT Innovations have characterized by innovation and by using continuous research and development as a competitive advantages in the market. Some of our innovative technologies include the development of advanced ultrasonic methods to inspect highly attenuating materials including castings, composites, and others. Our group helped in 2003, RD Tech, now Olympus NDT or Evident, on the development of advanced applications for the newly development of the Omniscan platform while it was still under development. These early units had then not only phased array and time-of-flight diffraction capabilities, but also advanced eddy current array technology. When the OmniScan was finally launched into the market, we did acquire some of the first units ever built. We purchased from Art D Tech some of the first OmniScans ever manufactured. This was in 2003. We started using this technology in the mining and petrochemical industry since the beginning of 2004. Our first advanced ultrasonic jobs consisted of corrosion mapping of petrochemical and natural gas pipelines. We were able to test, for the first time, thousands of miles of pipelines with this phased array and TOFD technology. We were also pioneers in the development of electromagnetic applications, and in particular of advanced eddy current array solutions. We have been the world leader in the development and continuous improvement of the technology required to inspect high-density polyethylene, PVC and composites by phased array and time-flight diffraction. We have worked in various projects around the world, working for large engineering and construction companies such as Fluor, Aker Kværner, Jacobs Engineering, Ames Construction, George Fisher, and many others. Using these technologies and working around the world for these companies, we had the opportunity to be the advanced NDT services provider, involved in the construction on all the new mining projects in the Americas since 2004, and in the USA in the construction of the first new mines in decades since 2006. We also were selected to be the non-destructive examination company for the biggest natural HDPE natural gas pipeline ever built till now. Thousands of miles of HDPE piping, materials, and welds inspected makes this project developed by us in Australia very innovative, complex and unique. We did several other innovative projects, such as testing, using advanced ultrasonics, of the welds, during construction of the first nuclear reactor cooled with HDPE piping. The list continues with many projects for Intel, and also in the defense and aerospace markets. We were awarded the first AWSD 1.1 project ever done using advanced ultrasonics. This project began only a few weeks after the American Welding Society allowed advanced ultrasonics to be used in the inspection of steel structures. The project consisted the inspection of all the welds during the construction of the dock and complete marine facilities for an LNG project. More than 10,000 miles of welds were inspected by phased array, time-of-flight diffraction, and multi-channel ultrasonics during this project. Evidently, we innovated, developed, and qualified several innovative, advanced ultrasonic inspection technologies for testing these structural welds in order to be able to execute this project. Since this project was the first of its kind in the world, we were visited and audited by several NDT experts from Europe and the Americas. We provide worldwide proven inspection solutions designed to perform pressure vessel, weld inspections, which comply with the most demanding construction codes. We design inspection solutions and configurations to fit each application need, TOFD, phased array, digital radiography as well as other electromagnetic superficial methods and techniques. We were awarded in 2008 the first advanced ultrasonics project in the United States of America to inspect petrochemical vessels, involving the use of advanced ultrasonics of complex vessels and stainless steel layered vessels for ExxonMobil and later for Shell. We competed for this job with several large inspection companies and were awarded the job by Jacobs Engineering due to the fact that we achieved the highest probability of detection during the qualification tests. The versatility of our technologies and equipment allow in-service inspection of pressure vessels containing hazardous materials. The meticulous qualification process of the inspection procedures prior to performing the inspection permits adjusting the system to the specific needs of each project, thus yielding reliable results even without the removal of the protective paint layers on the vessels. The periodical inspection of horizontal, spherical GLP and hydrogen vessels is very common based on maintenance management concepts such as API 579 and 580 fitness for service. We supplied proven solutions designed to perform pressure pipelines, weld inspections according to approved codes of construction, such as ASME B 31.3, ASME Section 5, Article 4, API 1104 and others. Designed to fit each pipeline welding configuration, whether for manual welding or for automated welding processes, multiple phased array, multiple TOFD, zone discrimination technologies, digital radiography, as well as the implementation of conventional and advanced electromagnetic array superficial methods and techniques. We also design and qualify custom-made NDT solutions for these applications, also aimed to meet each customer's specific needs at the field. Some of these technologies are used for corrosion detection applications. The mission of the Battleship Texas Foundation is to preserve and enhance the Battleship Texas and develop this historic ship into a premier museum and visitor attraction. Materials Research and Technology had the opportunity to help with the initial inspections of this vessel, specially confined areas under the boilers, in order to determine the condition of this vessel before it was taken to the dry dock for repairs. Battleship Texas is undergoing now the necessary repairs in order to save this ship for future generations and fulfill the mission of this foundation. Application of guided waves technology to avoid unnecessary excavation, coating removal, or scaffolding unless flaws are detected. Inspection of high-temperature insulated pipes, and many others. Strategically, we decided to focus our efforts on becoming the NDT company of choice for the mining sector, which extensively uses castings. Mining equipment is usually heavier and made of highly attenuating materials, such as castings and plastics. These materials are hard to test with conventional NDT equipment. We concentrated our efforts in the development of specific techniques to enable us to perform inspections of these highly attenuating materials. It was between 1998 and 2001 that we developed new solutions which allowed us to inspect such highly attenuating materials, including manganese steels, high chrome steels, and plastics. In 2003 to 2004 we acquired advanced ultrasonic equipment with phased array and TOFD capabilities. We developed the know-how and technology to design and build advanced mock-ups to inspect large castings. The ability to inspect heavy, highly attenuating materials, and the use of advanced ultrasonic equipment represented another breakthrough in the area of testing difficult castings. Our commitment to R&D, better procedures, extensive use of mock-ups, the use of high sensitivity and high-resolution transducers were strategic actions that gave us technological advantage in the global market for the inspections of castings and positioned our company as the supplier of choice in the world's castings testing market. Presently we are testing steel and cast iron castings for the largest castings manufacturers and end users in the Americas, Europe, Asia, and Australia. Since 2004, we have inspected thousands of SAG mills, ball mills, and crushers in the USA, Europe, China, and Australia for large mine expansion projects around the world. We are recognized as the NDT provider of choice by the most important manufacturers of mining equipment, such as FL Smith and Metso Minerals. The need to guarantee the integrity of the base material of structural and engineered plastic piping, such as HDPE and PVC, coupled with the need to detect or prevent defects during the welding process, whether by thermal fusion or electrofusion, led Materials Research and Technology and its sister company NDT Innovations to develop new technology and procedures in order to inspect these materials. We were the advisors for the ASTM Committee for the development of the ASTM E3044 standard practice for ultrasonic testing of polyethylene butt fusion joints. We developed advanced hydroelectric testing technology, the use of new microalloyed structural steels such as ASTM A516, 517 Sumiton, has permitted to reduce significantly the weight and sizes of the pressure pipelines in hydroelectric projects. There are more elaborate design criteria associated with these steels, as indicated in the Boiler and Pressure Vessel ASME Code, Division 2, as of 2010 edition with 2011 addenda and presently in the latest edition. The TOFD in phased array technologies, developed by us, have demonstrated a high probability of detection for welds in these engineering applications, which is even higher than the probability of detection with advanced industrial radiography. In 2009, Materials Research and Technology and its sister company NDT Innovations designed a semi-automatic inspection system for ultrasound applications in pressure pipelines for hydroelectric projects. Materials Research and Technology and its sister company NDT Innovations use advanced electromagnetic inspection technologies. We are capable to provide inspection support and guarantee of integrity for mining and petrochemical equipment in typically short time frames during maintenance shutdowns. The versatility of the methods we apply allows us to achieve a very competitive flaw detection capacity, even over thick layers of paint or lubrication grease of moving components, such as gears, mills, chassis, conveyors, among other components. Advanced electromagnetic inspection systems of multiple technologies, including eddy current, magnetic flux leakage, near-field testing, and remote field testing, eddy current array, and others in order to inspect with the highest reliability the fabrication and in-service inspection of such units as air conditioners, heat exchangers, boilers, and superheaters are commonly used. Alternating current field method of measurements, or ACFM, is also used to support the mining and petrochemical sectors. Failure analysis and material characterization. The performance of materials and components depend, to a large extent, on its own composition. We need to ensure that the materials used in any project are in accordance with the requirements for which they have been designed and meet the project specifications. Materials Research and Technology offers to the mining, industrial and construction sectors a series of equipment with extraordinary capabilities to analyze and verify if the materials used or to be used in a project meet the physical and mechanical criteria for the application that is being used or intended to be used. Materials Research and Technology counts with a state-of-the-art laboratory, manned by a group of scientists and engineers, which are exclusively dedicated to perform research of new material testing technologies and materials characterization. The result is the continued development of techniques and solutions not only for NDT applications, but also in a much broader aspect, for practical applications in the area of materials characterization and analysis in the industries that we serve. Applications with SEM electronic microscopes GEOL of 20 and 30 kV with EDS, WDS and EBSD. Development of analytical models and development of proprietary software and hardware. Forensic engineering. Tribology, major types of wear, including abrasion, friction, adhesion and cohesion, erosion and corrosion. Mechanical testing, stress and strain. Chemical analysis, OEE, XRF. Toughness is a mechanical property that depends on the elemental chemical constitution, as well as the microstructure and physical properties of the structural materials. The traditional tests for the determination of toughness require the destruction of part of the part or component for the production and manufacture of test pieces, which are subjected to impact tests or fracture mechanics, to obtain the tenacity of the piece, with respect to the sample. These destructive tests are known as CHARPY and covered on ASTME 23-12C. The absorbed energy shall be taken as the difference between the energy in the striking member at the instant of impact with the specimen and the energy remaining after breaking the specimen. This value is determined by the machine's scale reading. Important number of fragile failures worldwide are happening on components which have been tested using the CHARPY test. We identified a global problem and the need to develop a non-destructive method to measure tenacity because of the unexpected occurrence of failures, breaks, fissures, in the integrity of structures such as bridges, high-voltage towers, tanks, pipelines and accessories, elbows, reductions, etc., of steel to transport hydrocarbons, gas, oil, chemicals and mining pipelines, due to low tenacity in materials, generating material, personal, economic and environmental losses. We developed a new non-destructive testing technology to determine toughness. At present we are finalizing the development of new ultrasonic technology to determine toughness in steels. The correlations developed by us have been blind tested by several engineering and petrochemical companies and proved to have an extremely high correlation. Decades of experience in the industry makes us the perfect partners to provide NDT, API, and safety training in a completely different and new way of learning. We are recognized for our innovative and breakthrough ways of delivery through realistic simulations applicable in real life. We have developed innovative training tools in 3 different levels of expertise that cover theory and practical knowledge to prepare non-destructive testing personnel to excel while working on NDT inspections. Simulation and integrated-based learning. We are committed to deliver the most impactful and effective training techniques for all students with different learning styles and preferences, reinforcing visual/auditory and kinesthetic learning, such as instructional videos, which are so innovative our students learn the most complex concepts in a very absorbable way. We use simulators with realistic exercises, combined with activities that exploit the endless passion for excellence and innovation. Our students are thrilled by the depth of understanding that they get with our learning tools. Realistic, experienced, and technology-based approach. Innovation is in our DNA. We are proud to have the most leading-edge technology in our 2 labs in the continent. We are present in the USA and Latin America to serve from here all English and Spanish-speaking students. Our labs are equipped with world-class equipment and technology in Houston, Texas, and Lima, Peru. We are proud of giving the opportunity to our students to have access to very innovative equipment, such as an advanced computer tomography machine, for learning and research purposes, which is a very unusual opportunity to get in training the market. STEAM approach. We have designed and developed a STEAM learning approach that trains science, technology, engineering, and mathematics concepts to maximize the access points that guides the student in inquiry, dialogue, and critical thinking, integrating these principles through arts design. We have taken STEM to the highest level. It is a demonstrated approach to help students take thoughtful risks, engage in experiential learning to secure assimilation of complex concepts, persist in problem solving, and work through the creative process. Since our purpose is to transform the working lives of our students, we need to prepare innovators, leaders, and professionals that excel in their respective industries. We are close to receive ISO 17024 certification in order to perform training, qualification, and certification of personnel as per ISO 9712, this, in order to supply this important certification in countries where it is not available. CT scanning, metrology, and advanced computer-aided analysis. Materials, Research and Technology perform CT scanning to help clients, using a variety of advanced technologies, including reverse engineering, volumetric analysis, thickness measurements, advanced flaw detection and analysis, dimensional inspection, porosity detection and characterization, among others. Industrial computed tomography is a 3D imaging technology that captures multiple micro-focus, high-definition X-rays of a sample along a rotating axis. These images are later processed, and a high-detail 3D reconstruction of the object is obtained. This allows for a detailed imaging analysis of the subject without physically harming it. Several metrology analysis and simulation softwares are used to obtain accurate quantitative data from the 3D volume. This technology segments and isolates parts for further studies. Houston Corrosion Testing Services. Accelerated Stress Corrosion Cracking Analysis. Accelerated Corrosion Fatigue Testing. Testing for stress corrosion cracking. Use corrosion analysis and testing to get ahead of the problem. Soil and water testing for microbial corrosion. Cathodic protection simulation. Hurricane damage assessment and corrosion analysis. Expert witness services for corrosion and metallurgy. Metallurgical engineer expert consulting. Corrosion testing for additive manufactured components. Thermal diffusion galvanizing. Chemical composition analysis. Optical emission spectrometer calibration standards. The battle against corrosion. Quality assurance. Stress measurement in metals and materials. Stress measurements are required to ensure sufficient strength and safety of the equipment and infrastructure that we use on a daily basis. Strain gauges are widely used as one of the most accurate and practical methods for stress and strain measurements. Stress refers to the force that tries to maintain the initial shape of an object, yet stress is an internal force within objects, and the force cannot be measured directly. Strain gauges are designed to measure strain, in order to determine the associated stress, when a force is applied to the component. When a strain gauge is bonded to a surface under stress, it will distort, or flex in unison with the surface, causing a shift in electrical resistance proportional to the strained surface. The deformation of this material as it increases and decreases in length is called strain. Strain gauges detect this strain as a change in resistance. The strain gauge sensor is made of a metal foil, and its electrical resistance can be measured when passing a current through it. The component being tested deforms when external forces are applied to it, and this increases or decreases the resistance value. These characteristics are used in strain gauges. Strain gauges come in many different configurations. Choosing the right strain gauge for your application depends on which direction the primary strain is running, what type of strain you are measuring, and the target measuring area. The change in resistance can be accurately measured using a Wheatstone bridge.
The Wheatstone bridge was invented by Samuel Hunter Christie in 1833 and improved and popularized by Sir Charles Wheatstone in 1843. Samuel Hunter Christie, March 22, 1784 to January 24, 1865, was a British physicist and mathematician. He was particularly interested in magnetism, studying the Earth's magnetic field and designing improvements to the magnetic compass. In 1833, he published his diamond method, the forerunner of the Wheatstone bridge, in a paper on the magnetic and electrical properties of metals, as a method for comparing the resistances of wires of different thicknesses. However, the method went unrecognized until 1843, when Charles Wheatstone proposed it, in another paper for the Royal Society, for measuring resistance in electrical circuits. Although Wheatstone presented it as Christie's invention, it is his name, rather than Christie's, that is now associated with the device. Sir Charles Wheatstone, February 6, 1802 to October 19, 1875, was an English scientist and inventor of many scientific breakthroughs of the Victorian era, including the English concertina, the stereoscope, a device for displaying three-dimensional images, and the Playfair cipher, an encryption technique. However, Wheatstone is best known for his contributions in the development of the Wheatstone bridge, originally invented by Samuel Hunter Christie, which is used to measure an unknown electrical resistance, and as a major figure in the development of telegraphy. Measurement is one of the important aspects of science. It is difficult to conduct experiments and form theories without the ability to measure. Thus, to measure unknown resistance, capacitance, inductive reactance, or impedance in a circuit. A Wheatstone bridge is an electrical circuit used to measure an unknown electrical resistance by balancing two legs of a bridge circuit, one leg of which includes the unknown component. The primary benefit of the circuit is its ability to provide extremely accurate measurements, in contrast with something like a simple voltage divider. The Wheatstone bridge illustrates the concept of a differential measurement, which can be extremely accurate. Variations on the Wheatstone bridge can be used to measure resistance, capacitance, inductive reactance, impedance, and other quantities. The concept was extended to alternating current measurements by James Clerk Maxwell in 1865 and further improved as Blumlein bridge by Alan Blumleinen. A Wheatstone bridge circuit consists of 4 arms, of which 2 arms consist of known resistances while the other 2 arms consist of an unknown resistance and a variable resistance. The circuit also consists of a galvanometer and an electromotive force source. The voltage or electromotive force source is attached between points, while the galvanometer is connected between 2 other points of the bridge. The current that flows through the galvanometer depends on its potential difference. The Wheatstone bridge works on the principle of null deflection. This happens when the ratio of their resistances is equal, and no current flows through the circuit. Under normal conditions, the bridge is in an unbalanced condition where current flows through the galvanometer. This condition can be achieved by adjusting the known resistance and variable resistance. A Wheatstone bridge is said to be in a balanced condition when no current flows through the galvanometer. This condition can be achieved by adjusting the known resistance and variable resistance. The bridge is said to be balanced when no current flows through the galvanometer. In this case we have a higher resistance in one side of the bridge, so there is an unbalance in the bridge, and current flows through the galvanometer. In this second case we have a lower resistance in same side of the bridge, so there is again an unbalance in the bridge, but in this case the current flows through the galvanometer in the opposite direction. The Wheatstone bridge circuit is nothing more than two simple series parallel arrangements of resistances connected between a voltage supply terminal and ground, producing zero voltage difference between the two parallel branches when balanced. The Wheatstone bridge diamond-shaped circuit and can be used to accurately measure unknown resistance, capacitance, inductive reactance and impedance values, or as a means of calibrating measuring instruments, voltmeters, ammeters, etc., by the use of a variable resistance and a simple mathematical formula. Eddy current instruments use bridges in order to compare the difference impedances between coils attached to both sides of the bridge.
Materials sciences and non-destructive testing in the defense industry. Non-destructive testing uses a wide group of techniques applied in science and industry to evaluate defense assets without causing any sort of damage or alteration to them. Also known as non-destructive examination and non-destructive inspection. NDT is a highly effective way to assure asset availability, performance, and operational safety. Due to its capability to detect the very smallest of discontinuities, imperfections, or damage in defense structures, equipment and components, it's widely used. Non-destructive testing methods include ultrasonic, electromagnetic, radiographic, remote visual inspection, guided waves, magnetic particle, penetrant testing, and others. All these advanced technologies can be used to detect defects such as geometrical faults, material thickness, welding defects, delamination, porosity, foreign objects, cracks or corrosion.